Alright, so this video is about limits. Your book actually calls it limits at infinity. I prefer limits involving infinity. And you'll see what I mean momentarily. Okay. First of all, let's get an idea here. The idea of a limit means there's a cap on something. Infinity or infinite means there is no cap on something. And so that's going to be something that, when we talk about these things, you got to keep that in mind. So if you saw this function with an asymptote right here, let's say this is x equals 3. If you see the function, obviously not touching the asymptote, getting very close to it, what is the limit, if this is f of x, what is the limit of f of x as x approaches 3? Well, it's going up, it's unbounded, it's headed towards infinity. I would say it's infinity because it's going up, and it's going up how far? All the way. This is what I would call it. Now, some books, some calculus books, say that this limit does not exist. And the reason it does not exist, they say, is because if it's going to infinity, that by definition is unbounded. So therefore, the limit does not exist. I don't like that because guess what? That does not exist. This is also one of them going down and one of them going up. This is also does not exist. This also does not exist. So is this one. They all are does not exist. This tells me what's happening. It is headed towards positive infinity. And that's how I would prefer that you write them. Okay? Now, and we can look at another one here, 1 over x. What is the limit as x approaches 0 of 1 over x? Well, look at the graph. There's an asymptote. What is the limit? The limit does not exist. And the limit does not exist because the left-hand limit is going to negative infinity. And the right-hand limit is headed towards positive infinity. And because they are not the same, the limit does not exist. Okay? Those are pretty straightforward. What happens at asymptotes is easy money. What's a little trickier is, this guy isn't very hard. This guy isn't very hard. We'll do one more ego booster. What happens to this function, x squared plus 6x minus 1? What happens as x approaches infinity? Let's see. A huge number squared plus 6 times a huge number minus 1, whatever that means. This thing, the limit is infinity. It's going up forever. And I recognize that because when I graph this function, as I go this direction on the x-axis, my y's are going up. Furthermore, what happens is you go the other direction to negative infinity. Well, because it's x squared, it is also going up, going this direction. So as x goes there, y is also going up. Okay? Nose. Not very hard. Now, what if you take this one here? This one's a little trickier. The limit as x approaches infinity of 3x squared plus, why did I do that one? What happens to this thing as x heads towards infinity? Okay. Well, one might astutely realize that as x gets huge, these pieces right here don't mean much anymore. Okay? When you were a kid, a penny was a lot, and then you started being, you're all fancy now, you throw pennies on the ground. Keep your penny, I don't want it. And then you start making more cash, and you're like, well, I can tip a few dollars, and then later on, next thing you know, you're throwing 50s around like they're nothing and whatnot. And the more money you make, the more it goes up. Like Bill Gates, drops $50 on lunch, probably doesn't think about it. Okay, I might spend $50 on a dinner sometime, but it'd have to be a very fancy dinner. It'd be once in a blue moon kind of a thing. Yeah. As x's gets huge, these numbers here, they don't mean much. Intuitively, we know that to be true. But we're going to develop a pattern or a formula for these things. So, when you have a function like this, what you want to do is identify the highest power of x in the denominator. Okay? Because what you're going to end up with is infinity over infinity. And we have a way to deal with that in a few chapters, well, in the next chapter. Actually, chapter 4, I guess it is. There's another way to handle this problem. But intuitively, I mean, the thing's going to infinity over infinity. Now, you might be tempted to say that's 1, but you'd be wrong. So how do I fix this? Well, the rule is you find the highest power of x in the denominator, and you multiply by 1 over that. And you do it on the top and the bottom. Remember, this is just a fancy way of saying 1. So you're going to get 3x squared over x squared plus 4x x squared plus 1 over x squared over x squared over x squared plus 4 over x squared. Yay! Now, remember, the limit laws say that the limit of a quotient is the quotient of the limits. So I can pass that through and look at the quotient of the numerator, which I can simplify before I do that. And look at the quotient of the, or the limit of the denominator. And of course, the limit of the sum is the sum of the limits. So what's the limit of 3? Well, the limit of any constant is 3. But wait, Jay, but what if it's this? What if x is this? What part of constant do you not understand, sir? That's what I say to you. So 3. So 3. Now what happens is 4 divided by a huge number, this piece here is headed towards 0. And you take a huge number, like say 1 billion, square it, that's really big. What is 1 divided by that? Well, it's headed towards 0, and it's getting there pretty rapidly. On the bottom, we're going to have 1, 0, and 0. So we would say that the limit is 3. Okay? It's pretty easy to do. Excuse me. All right. So you're like, well, what if you had this one? One could argue, again, that it's infinity over infinity. However, an astute person realizes that the top is getting bigger faster than the bottom because it's a cubic instead of a square. Again, the rule is you divide through by the highest power of x in the denominator. So it's going to be 2x cubed over x squared. And we're going to take the limit of each one of those guys individually. Okay? Now, before I get carried away, of course that's 2x minus 6 over x. Oops, 6 over x, I said. Plus 1 over x squared. That's 12 minus 3 over x squared. Okay? Well, the top, these two pieces are going to 0. This piece is 2. But what you're going to end up with is the top is getting huge, headed towards infinity. And what is infinity divided by 12? Well, it's ridiculous. It's infinity. So what we're saying here is this function, the limit, is actually infinity. If you were to graph this guy, I don't know what happens over here. But in general, that function tends to head upwards. Okay? Now, of course, the guy can check this on Desmos pretty easily, or whichever your favorite graphing calculating device happens to be. So 2x cubed minus 6x plus 1 divide by 2x, oops, I said divide by, there you go, 2x squared, oh, it's 12x squared, sorry, 12x squared minus 3. I don't know, again, I don't know what's happening over here around 0. I don't care. But look what happens as x goes to infinity. This baby is going up and it's never coming back. Okay? Now you might remember back in, Algebra 2, pre-calculus, you might have had a teacher that said to you, you have what is called a slant asymptote. This is a situation where we have that. Oh, Jay, where did that come from? Check it out, dude. Everything else tends to cancel off here and here, yes? And you're left with 2x divided by 12. Interesting to note that as x goes to infinity, as you're headed out this direction, those two lines become almost inseparable. They are both headed to infinity. Okay? Excuse me. Goodness sakes. Well, you're like, well, what happens as you head toward negative infinity? Well, let's find out. Well, clearly, it doesn't matter if you're dividing by a big positive or a big negative number. Those two pieces are still going to 0, as is this guy. But this numerator will be headed towards negative infinity, which is exactly what the picture shows. As you're headed out this direction, they're headed towards negative infinity. I don't care if you know the term slant asymptote. I just think it's a nice tie-in occasionally. How about this one? What is the limit as x approaches infinity of 3x over x to the 4th plus 1? Now, again, an astute individual realizes that denominator is getting bigger way faster than the numerator, and you're right. So, if a fraction, the bottom's getting bigger, well, the whole thing must be headed towards 0. Goodness, I've got allergies going on tonight. Maybe it's a cold. That's no bueno. All right, so here we have this. Here we have this. All right. Cool. Now, this on top becomes 3 over x cubed. On the bottom, we have 1 plus 1 over x to the 4th. Now, what is the limit as x goes to infinity of these pieces? Well, the bottom is going to just 1. But the numerator is going to 0, meaning the entire fraction is going to 0. And if you graph that guy, that's exactly what you will see. Something like that. Right. But Jay, what about these peaks? Yeah, what about them? Okay. Well, what do you mean? I'm like, infinity is way out here. Look at this line. It's hard to get much closer to 0. In fact, the computer just punts and says, screw you, it's 0. Now, you're here at 35. Friends, okay, it's not 0, but it's really close to 0. How close to infinity are you? Well, you're not very close, okay? And so if you come in here a ways, you can see that even in here right around 4 or 5, why, it's tiny, and it's headed towards 0. And about here, it just says, oh, screw it, let's just call it 0, right? Right around there, okay, a little more. Right around in here, right around 18, it just says, oh, screw it, let's just call it 0 now, okay? And so that's the idea of limits as you approach infinity. Very easy to do. Just that cute little